Now that was quite some applause, which worries me a bit because then we will be able to measure the success of the talk by comparing it to the applause afterwards. But we'll see. Okay, so I'm Simon Kågström. I'm a consultant. I work mostly with embedded systems, and I currently work at Profoto with studio lighting, basically. Should I shout more? Okay. Today I will talk about the disassembler. I had a talk for C++ meetup a year or two ago, or so it felt, but it was actually 7 years ago. It turns out now. So we'll see when the next one is, but maybe around 2030. But this is this one, and I will actually start with a demo. And at first, I've written a disassembler, and maybe some of you are asking why would I use this one instead of Gehidra or the compiler explorer or something else. And my answer to that is that you probably shouldn't. The other ones are probably better, but with software it's very nice that if you have an idea, all you need is a computer. You can just implement it completely free. You don't need any expensive stuff apart from the computer, which you probably already have. So that's at least my motivation. Something fun to work on, and then you can do something with it. Now let's see if I can. Sorry, I need to do like this. And we should do there. Okay, then. Sorry, not NM. There. But it doesn't matter. It's just a terminal. I open a file from there. So we'll see if it works. It did, but it came up in the wrong window here. Here. Okay, so this is the application. I just wanted to show it before starting to talk about stuff. And what you see here is symbols in the file. You can also show the sections in the file. And then the interface is basically inspired by Wireshark and a web browser. So you have this filter or location bar here where you can search for symbols or type in addresses. So the application is a sort of calculator. So I can filter and then find some symbol to disassemble, which I have here. And then here to the right you have the cross-referencing. So you can see that this one has been called from main, and then it also has a lot of self-references because there are jumps within it. And you have the other way calls from that one. And then, you can look at the instructions in here, and you have the source code at the bottom. And some illustration of where jumps end up. And you can go between functions. So that's basically it. I will try to get back to the presentation. So the outline looks like this. I will go back a bit and motivate why I think at least I needed this. Then I will talk about what you actually need to write the disassembler. And then the third part is some sort of software engineering. Why is it easier now than it was 10 years ago? And I'll start with the motivation. Why bother with disassembly at all? And why write a graphical disassembler? Well, it turns out, at least for me, I have at some points during my, I wouldn't say career because it has been mostly private stuff, but I have multiple times ended up in situations where something might be very difficult to debug, or that basically needed a disassembler to understand how things work. And one special case is with inline assembly, which I used to do a lot of in a project I worked on almost 20 years ago now, so a long time ago. And this is part of how it looked. This is GCC inline assembly. And the tricky part with inline assembly is that it's very powerful, and you can make small mistake and you start your program and it works perfectly. And then you maybe add some lines of code or remove some lines of code and then recompile it and start it again, and it fails in the most amazing ways, and very difficult to understand what actually happens. And in that case, it's very nice to be able to disassemble the code and try to understand what it does, because if you make an error in the inline assembly, then you need to check what did the compiler actually make out of it. Because with the GCC inline assembly like you have here, you have basically three parts. You have inputs to the snippet, you have outputs, and you have something called clobbered. And clobbered, I had to look up what it actually means, and it means to hit someone or something hard and repeatedly, which also I think summarizes inline assembly a lot very well. And so I had that sort of problems, and I had to disassemble the code and look at, here I can see that the compiler then reduced one of the registers that I just trashed in this function. And that was maybe because I had made a mistake in the clobbered section there. So something like that. And then the second thing was that I also wanted some sort of navigation to be able to quickly go between places or follow the code like you saw in the example I had before. So just using object dump, that was, at least I think, a bit tedious, so I wanted some graphical tool. So I wrote a small Python application, which is the one on the left there, which is just or parses text output from NM and object dump. So very simple graphical front end, and worked well enough for what I had then. This was also, by the way, in 2006, so it's very old. So it worked well enough, but the problem with that one was that as soon as you gave it some larger program, or like, the Linux kernel or something, it would completely fall over. So I thought, since I was, for the first part, using or writing stuff for the Linux kernel at my day job, and then the second thing was that I was using a lot more C++. I thought that, well, why not rewrite it in C++ and then use this libbfd, which is the library object dump uses as a library instead, and then use it that way. And that's the one on the right there. And the name of it, the name of the one you saw here as well, is Emil Pro, not because it's professional, but because it's a pun on the EDA Pro, which, at least back when I started, was the state of the art. Now the problem was that I got this one working well enough, but for reasons I hope to get back to, it bitrot very badly, and when I then, just the other year, got into an issue which I needed a disassembler for again. This time it was C++, and the question was how can this code compile to 14 kilobytes? So I thought I'd try to revive that one, and yeah, that's the topic of the rest of the talk. Okay, so now already on part 2, what do the disassembler actually need? So at first, there are many binary formats which are used for executables, shared libraries, linkable object files. And I think these are the most commonly used today. So ELF, which is used in Linux, FreeBSD, or at least I think it is FreeBSD still, and a lot of other systems. Also for embedded system, it's typically used as an intermediate format. And then this Mac OS have the Mach-O, I think it should be pronounced, but I guess everyone says Macho. So yeah, you can see that the authors of this format have some sort of humor. There's also the dwarf debugging format. So if you'd like, I think you should add a orc format somewhere. And then Windows maybe being the exception to this rule, since they just call their format P. Yeah, okay, so a lot of formats. And then, well, how do you write it? I did not write everything from scratch, as I indicated before. So it's like Newton says, if I hadn't been standing on the shoulder of giants, I wouldn't have reached the apple. And basically, there are 3 main parts which I build it on. Qt as the graphical library. And then this libbfd, which is used for parsing the binary files. And then Capstone, which is a disassembly library that disassembles the parts that I get from libbfd. BFD stands for binary file descriptor, by the way, and is part of binutils, where the linker also is. Okay, but already there's been some details, so I thought I'd take a small step back. So basically, the question here is, you have some sort of binary, maybe an ELF file, which has the ELF magic there, and you want to get the instructions out of it, and hopefully in a understandable format. Okay, so both views here show the same thing. It's just easier to be able to point to stuff via both of them. Depending on what kind of binary you have, you might actually already be done in this case. At least if you have some MS-DOS COM file, which doesn't have even a header. It's just the instructions and data. So then you can start disassembling by just opening the file. But for most formats, you want at least or need some more parsing than that. Okay, so the sections are the basic blocks or basic building blocks of the ELF file. And similar concepts, I guess, are present in most other binary formats. And this is the first thing we'll want to or need to find our instructions. And again, if just getting to the instructions is our only goal, then we can stop here. Because you have the section there, or the section headers, and some info of the section, namely some flags indicating the type and so on, and an offset into the file. You also have name and whatnot there. And with this offset into the file, then you can disassemble the section immediately. And if I open an MS-DOS file with it, this is what I will do, because there's not very much more to go with. But there are some disadvantages with just disassembling the sections immediately. Well, first of all, you will only get out instructions and not very much more data than that. But there are some other issues that maybe someone in the audience might guess. Someone know? Why is it difficult to just, yes?
Program headers that don't belong to a section?
Maybe not so much program headers, but well, how do you know what are instructions in the section? For many instruction sets, the compiler will generate code and data, and mix them because, for example, on ARM, the thumb mode, the instructions are so small that you can't fit an entire address in an instruction. So they put the addresses at typically at the end of the functions. So it's quite easy to get lost on when parsing the instructions in this way. Especially on some architectures like x86, which have variable length instructions. And I guess actually, maybe for the next talk, I think this is something where machine learning can probably do wonders to identify that these are probably instructions. So anyway, since I'm mostly interested in using it as a debugger, I want something more, and that is the symbols. Okay, so the symbol data can be found in a section of their own. So that's what the top arrow here shows. The symbols are functions, they are global data, and can also be stuff that the compiler and linker uses to tag stuff with. So there are lots of different types of symbols. I mainly care about the ones which are executable. And the symbol, they have a reference to a section, and they have an offset into the section. There is actually also size, but you can't really rely on the size because it's optional and sometimes filled in and sometimes not. So what I do is, sort the symbols and in the section with basically just an STD map. And then the size is one symbol to the next one. It might not always be exactly what the compiler intended. You might get some extra data after it, but it's good enough. Okay, so with symbols then, we can get some, or to the good stuff here. Namely the instructions. So when you have the symbol, then you can disassemble instructions and have them refer to this symbol. And the disassembly, as I said, is done by this capstone library. And apart from the text output of the instruction, you also get some metadata with it. So in particular, I'm interested in basically two things, registers that are used and then what type of instruction it is, especially branches and calls. And the type is used to illustrate these jumps with arrows. So then you have the instructions and then you think you would be done and ready for beer, but there is one more issue here. And this particular case has a call to printf. But where is printf located? And then, let's say this is an object file or an executable that links to a shared library. Then printf will not be part of this file. And therefore, we also want to parse relocations because the linker if it was an object file at least. The linker will have added the compiler will have added a relocation entry. And the purpose of them is really for the linker to resolve them when you link together the objects and fill in the address.
The runtime linker now?
No, I'm okay. Yeah, there are two. I was about to get to that. At first, the printf maybe was a bad example because that will most likely reside in some shared library. But if you link together object files, then this is done by the regular linker. And what it needs to do is basically patch up this printf call with an address, where it should go. And then depending on what architecture you have, you can also have multiple relocation entries for the same destination address. So what you have is a symbol and then an offset, and the offset points into here. For me, it's most interesting to get to the instruction. And then, with the dynamic linker, then it's also done in runtime to resolve shared libraries and so on. I guess this maybe, when I learned it, was mostly 32-bit systems, and at least on Linux, you have this PLT, or procedure linking table, where you would have the undefined references for calls into shared libraries in one place. Because otherwise it might be that you have 1,000 calls to printf, and then you have to fix all of them up. The advantage with this procedure linking table is that you only need to patch one place. But these days, I guess that position-independent executables are more common. And then, although I'm not really an expert in that, I guess that you will have to relocate a lot of stuff during runtime as well. Okay, what was I going to say? Yes. So where does it end up? And then this one is actually more of a, it's shown here as a section for undefined symbols, but actually I guess in most formats there is no actual section in the file for the undefined. But this libbfd, it handles it as a section. So what I see is an undefined section. And then the symbol for this undefined, well, printf in this case, which is in some shared library. Yeah, so those are basically all the parts that at least I needed to get what you have before there, or saw before. Okay, and then the final part, why I think this was a lot easier now than 10 years ago. And then I will shortly speak about the problems with the first version of this program. So the first mistake I made was feature scope. I had a lot of ideas, so like being able to edit instructions, and then they would be pushed to a web service to share with others and so on. Quite a lot of work, while at the same time some simple features like, resizing the window, that didn't work very well. Of course I did this in my spare time, so I did what I think was interesting, and it worked well enough for me. But anyway, it's it became complex and didn't all work out all that well. But then the second and more serious problem was with libbfd. There are two parts to this. The first is that it has very good documentation, libbfd, but there are parts of it which are quite difficult to understand, and in particular this goes for relocations. So when I started with this, I was only on Linux and wasn't very interested in other systems, and I thought that, well, I'd worked in other projects with relocations for ELF and just parsing the ELF file manually or with the libelf libraries. So that was simple enough. So what I did was basically just, here are the sections with relocations, just parse the ELF data. But that also made it ELF only, because I didn't use the library itself for it. So that was bad. I couldn't run it on my Mac, which I have now. Then the second problem is that libbfd comes in multi-arch or, well, single-arch, non-multi-arch variants. And I really want the multi-arch one because, I want to be able to disassemble something which isn't just for my own computer. And I used libbfd and not Capstone as a disassembler then, which sort of makes sense because there's a huge number of architectures it understands. It's like C3PO. But the problem then was that since the distribution, you can install the multi-arch one, but that only goes for the binaries, not for the library. The library is, or was at least, just a single architecture one. So what I did was, well, as part of the build, just build libbfd, which took an hour or so. And then because I didn't want to deal with like changes into it, I just pegged it to a version. And well, a few years on, it was impossible to compile. So therefore I decided for this new one that I wouldn't use libbfd. That has to be the distribution package. Otherwise, no. Okay. So the second reason why I think it's much easier now is, of course, C++. So I started the previous implementation at 2011, 2012. I wasn't very good at C++ 11, and well, the compiler I used also didn't support very much there, or at least not all of it. So it was based at first on C++ 03. And as you all know, there's huge difference programming in C++ right now. Not only that you get to write a lot more compact code, but things like lambdas that goes really well with programming with the Qt library when you do something on a signal. So I think it's a much better language. And then the second thing is that the infrastructure is a lot better. You see some Conan stuff, and Conan is also very nice because you are able to use the same versions of packages on, well, multiple OSs and builds, which makes it easier to maintain. I guess that maybe some distribution maintainers might not like Conan very much, but for us casual developers, it's very nice. And also actually on Mac, there was a very special place where I was helped by Conan. And here you can see that this libbfd is here. And that's because the libbfd on Homebrew, the distribution manager, doesn't actually ship or link with, it doesn't ship with libbfd. So linking with libbfd will just give you a lot of undefined references. And they have reasons for it, so I tried to get in a patch, but they didn't want it. So I despaired, but then found out that libbfd is actually part of the, or exists in Conan. So it was very easy to just add it there and link with it that way. It's some utility package that GNU uses. Okay, so a lot of that. Another thing which I also think has become much easier is that we now have the address sanitizer. I think maybe it was around when I started as well, but at least I didn't use it then. And yeah, it makes some of the difficult issues much easier to find early on. So I tend to use it at all the bug builds, even though it's quite slow. Okay, so then the final reason I think might be a bit controversial, namely AI. So I use this Copilot, and as I'll show you a few examples actually, if I can get them on the right screen here from the code. Oh, sorry. I need to do like that. And then this one. Here we have some code. Where am I there? Yeah, like that. Okay, sorry. Okay, so perhaps difficult to read, but these are parts of the unit tests. And yeah, it's for this how you write the lines or set up the lines for jumps. And yeah, I really need to visualize stuff, so I did some ASCII art here with some test case that I wanted to make sure it worked. So I set this one up and draw it with these pointers, and then I wrote some helper function here to just set up this case in the unit test environment. And then this part I didn't write. This was all filled in by this Copilot. And of course, I mean, I'm impressed that it can actually read what I drew up here. Of course, this is something that I could have done myself, but I probably would have made some mistakes in it. And yeah, I think it's really nice as a sort of autocomplete in that way. Then the second small example I wanted to show you is from Qt, or use of the Qt library. So I wanted to, when I press enter on an instruction, I wanted to jump to, if it's a call, to the one, yeah, the one you point to. And this is easy to do when you double click. But then how do you handle, how do I get that with, when I press enter? And then I Google for it, and yeah, there's some, because I don't really work with Qt in my day-to-day job, so I'm not an expert on that. So I Googled for it, and yeah, there is some event filter you should install and so on. But then from those examples, it was for me quite difficult to understand how will that work here. But well, just asking the Copilot, then it was easier. Then I just get some code that fits into my application and it works. You can actually see in the code that there's a lot more comments in the parts that the AI has written. And maybe sometimes a bit too much indentation as well. Okay, let's get back. Where am I there? Then some yeah, funny stuff. It also tried to help me with the presentation here, but that wouldn't turn out very well. It's difficult to read, but I don't know, it got into something, some loop there. So yeah, you had one instruction, you had the next instruction, and you had the next one. For some reason, it stopped at 12. Yeah. Okay, so this was actually all I had. But I have a small teaser for my next talk. So do we have any people from Uppsala in here? So did you know that you live in the edge case? No? Okay, we'll see the next time. Thank you. Yeah. So if there are questions, then feel free.
Do you deal with like trying to find out what is data and what is code, like by interpreting instructions and seeing, like, following the jumps and everything is left as data, or do you?
No, I don't. I intended to do for ARM because there it's tagged by symbols when you, or actually both when you switch from 32-bit ARM to this thumb mode, but also for this data. So I actually don't do that, but yeah, I intend to add it sometime. Yeah.
I see in your command file that you're still using FMT despite being on 23. Does that mean that standard format didn't work for you?
Yes.
Oh, oops.
On
It's,
Mac, still not really.
Yeah.
Oh.
Yeah. Maybe the next upgrade I can get rid of it. Yeah, okay. Anything else? Yes?
About your motivation, can you tell us more what kind of applications these were and like what kind of environments were you running them on? 'Cause I've never seen an app that needs so much effort.
Yeah, okay, so my motivation is mainly that I think it's fun to work on this stuff. It's not always useful. But the original motivation I had was I was working on a binary translator. And that was an environment where I couldn't use a regular debugger, so all I had was basically disassembling the code and yeah, reading the instructions and trying to make out what happened. I could get some back traces, but not more than that. So that was when I started a long time ago with it. Yeah, back there.
Did you ever consider hooking this up as a debugger for Sibyl?
Well, this one is after after that, but yeah, no, I didn't do that. I tried actually with some Java debugger to get, but I never got very far with actually having any use of it. Okay.
Tack Simon.
Tack.